Okay. Okay. So what we're going to do today is we're going to talk about bosons. So what we did last time was we dealt with non-interacting fermions, and amongst other things, I showed you why the grand canonical distribution is a good thing. Now, one of the things that we did was we wrote down the general recipe for writing down equations of state in statistical mechanics, where you write down the equation of state as in terms of a grand partition function that's shown over here on the left. And we write down the constraint equation. The constraint equation determines the chemical potential for us, and then we substitute that into the equation of state, and therefore we can work out the equation of state exactly, for at least for non-interacting systems. And last time I introduced, we did the integrals of sum over states. We did those as integrals over K-space, and from that, then we were able to take out all the numerical parameters by changes of variables and reduce it down to the form like this, where the equation of state for P and for the number is written down in terms of an integral which has as parameters beta and m, and then the spin degeneracy and Planck's constant, and then we parameterize those integrals in terms of a function which I call f5 halves and f3 halves. So I wrote down those functions for you, wrote out the Taylor series expansions for them, and then also told you about the asymptotics of those functions, f3 half in particular. I didn't tell you how I got the large Z behavior, but that's not important. What's important is the small Z behavior, and so we looked at we could then have in principle a way to write down the exact solution for these non-interacting fermions. And then at the end of last lecture, what I did was I showed you that this quantum equation of state in the high temperature limit reduced to the classical equation of state. Okay, it's not obvious that it would do that. Up to now, we've done it by saying, well, the occupancy at high temperatures at the average occupation of a state is going to be very small, and so we can just make that approximation, and then we end up with the Boltzmann distribution. But now we're doing it in a very formal way. So the constraint equation I showed you was written down as in the form in the middle of the page here on the left. So the thermal de Broglie wavelength cubed over the volume per particle, that's a dimensionless number. It's normalized by the degeneracy factor 1 plus 2s when the fermions have spin s. And then that is just this function f3 halves of the fugacity lambda, which is then e to the beta mu. And so what I showed you was that when the left-hand side is very small, namely lambda thermal de Broglie wavelength is much smaller than the volume per particle, what that means is that the distance between particles is much larger than the sort of quantum fuzziness of the particles. And so that's the classical limit. And because the function on the right-hand side, the f3 halves function, looks like I've drawn on the top of the left-hand panel, what that means is that we're just looking at the linear and next to linear behavior of that function f3 halves. So then what I did for you was I expanded f3 halves of lambda to second order in lambda in terms of the fugacity. And then what I did was I wrote the fugacity in terms of the thermal de Broglie wavelength divided by the volume per particle. So you can think of that parameter as being a small parameter, which is the parameter that is the expansion parameter as you're expanding around the classical gas and going into the quantum regime. And then what I showed you was if I then substitute the formula for the fugacity, that's over here in the middle of the page, I substitute that into the equation of state for the pressure. So here's the equation of state for the pressure somewhere over here. Here's the equation of state for the pressure over here on the left. So substituting that into the equation of state for the pressure, then I derive that PV over KT is equal to the formula shown over here on the left. In fact, what I did was literally divided those two equations. And then I showed you that the leading term is that PV over KT is equal to 1. That's the leading behavior. And that leading behavior being 1 is then equivalent to the ideal gas equation state PV equals NKT, because little v is equal to the volume per particle. So that's showing you that the first term, the leading term in the equation of state, is the ideal gas behavior. And then we've now got an expression for the correction to that, which is the behavior, which is this lambda cube term over here. And that correction, what we noticed was that correction is positive, and that then tells you that the fermions, as I go down in temperature from very large temperatures, you start to notice the effects of quantum mechanics. And in particular, you notice the effects of the Pauli exclusion principle. Pauli exclusion means that electrons or fermions don't want to be in the same state. So in effect, then, their pressure is going to be then greater than it would have been if they were ideal gas particles where they don't have any quantum effects whatsoever. And so we're now seeing the first evidence of a force, a measurable force, due to quantum mechanics, due purely to quantum statistics. And in bosons, that effect will be a negative pressure, because bosons do like to be in the same state, as you know from doing the principle of detailed balance for deriving the Bose-Einstein distribution. Namely, that the rate at which bosons will go into a state is increased if that state is already occupied by bosons. That was the thing that you worked out in one of the homeworks. All right, so that's great. And so now what we're going to do is section 2.93 in my printed notes. We're going to now apply the same formalism to non-interacting bosons. And so let us get started with that. So now we're talking about non-interacting bosons. And we're going to use the same formula. So the main idea is that the grand partition function is the same as for fermions, but for fermions, we had n was 0 or 1, the occupation of the state, whereas for bosons, it is 0, 1, 2, 3, all the way up to infinity. So this is for fermions, and this is for bosons. So now let's write it down. So we already know the dirty trick for solving these things quickly. So we will use the quick and dirty trick. The quick and dirty trick was that we already knew that the grand partition function will factorize into the grand partition function for each of the single particle quantum states. We proved that last time, or 2 times ago. We proved that by actually computing the grand partition function and seeing that by summing over the number of particles, which is what you do in the grand partition function, you actually make the whole grand partition factorize. That's why the grand partition function is a good thing. And that factorization has the meaning that each individual single particle quantum state is independent from the others, but they're interacting through particle and energy exchange. So that's why we can do this dirty trick. So we just say the grand partition function for a single particle quantum state labeled by I now goes from Ni is from 0 to infinity, and then the Gibbs distribution, which is epsilon I minus mu times Ni. And so this is a different, slightly different from the fermions. In the fermion case, we only had 2 terms, the n equals 0 term and the n equals 1 term. Now we have to sum from 0 to infinity. So this has the form of a geometric series. And so we can then just read off that we know how to sum, 1 plus x squared plus x cubed and so on. We know how to sum that. And so therefore we can write down straight away that chi I is then 1 over 1 minus e to the minus beta epsilon I minus mu. So that's just summing the geometric series. And then if I want to compute the average occupation number of the single particle quantum state I, so that is the expectation value of Ni, and that is then just 1 over beta d by d mu of the logarithm of chi I, and that then is equal to 1 over e to the beta epsilon I minus mu minus 1. And that is the Bose-Einstein distribution. And if we want to know what a mu is, well, we just have the constraint equation, sum of Fi is equal to n. So this is the constraint equation. And that's the solution to the problem. Okay, Jake, you had a quick question?
Yes, so in purple here, this is for one particle.
Single particle quantum state.
Yes, and then n is
the occupation of that state. It's a dummy variable that can be 0 up to infinity.
But doesn't that mean there's more, like, isn't that the number of particles in that state?
Ni is, this is if you like, the number of particles in the state. Fi is the average number of particles.
But isn't it a single particle?
It's a state that any single particle can be in, labeled by a quantum number like wave number, but it doesn't mean that only one particle can be in a state.
Right. Okay.
So remember, when you talk about single particle quantum states, as opposed to many body quantum states, we're talking about a quantum state where the many body wave function can be factorized into individual, into one body interactions. Okay? Did I answer your question?
Yes.
Thank you. Okay, so this is fine. However, I've glossed over one important fact. Can anybody tell me what did I gloss over that is an important fact to mention? So everything looks fine. Everything I told you is true, but there's one other fact that needs to be mentioned. Okay, yeah, Gabriel,
Mu is less than EI
why?
because R has in the geometric series, R is the end, R has to be less than 1.
Yes. In the geometric series, when you're doing, thank you very much. So when you're summing a geometric series, it's only going to converge if the thing that you're exponentiating, as it were, is less than 1. So the additional constraint is that e to the beta mu minus epsilon I must be less than 1, and that must be true for all values of epsilon I, including epsilon I is equal to 0. So for this to be true, that means that the chemical potential must be 0, must be less than 0. So the chemical potential in a Bose gas has to be negative. Remember what happened for the Fermi-Dirac distribution. The chemical potential, I showed you the numerical solution of that, started off as being positive and then gradually became negative for large temperatures. So here we expect the same thing. So what we expect that for large enough t, mu will be negative, just as with the Fermi-Dirac distribution. But here it is always negative. And we're going to see that that has important consequences. Okay, so now I just showed you the quick and dirty way to derive the Bose-Einstein distribution. Let's now write down the full grand partition function. So now let's do the full calculation. And as everything goes through exactly as we did for Fermi-Dirac, so you should check it. So the grand partition function, the full grand partition function, is then going to be the product over states of the sum from n equals 0 to infinity e to the beta mu minus epsilon I times n, like so. And then this then is equal to the product over states of 1 over 1 minus e to the minus beta epsilon I minus mu, like so. And then we can then work through the same calculations we had before. So then the equation of state is PV over KT is equal to minus the sum over states, the logarithm of 1 minus e to the minus beta epsilon minus mu. And the constraint equation is n is equal to the sum over I of 1 over e to the beta epsilon I minus mu minus 1. So everything there is literally just following what we did for fermions. And so I want you to check that, please. And so the next thing that we might do then is we will say, well, to evaluate these sums, we're going to turn the sum over I into a sum over k, and then I'm going to turn that sum over k into an integral over k, and I'm going to turn that integral into an integral over energy. Okay, so there's a sequence. We take the sum over state, that's formal. The states are specified by the momenta, plane waves. So those quantum numbers, that's the sum over k. We turn the sum over k into an integral over k because we're looking at the large system limit. So we can turn the sum into an integral. And then I'm going to make another change of variables, which we talked about, to turn that integral over k into an integral over energy using the fact that these are free particles. And so epsilon is just h bar squared k squared over 2m. So then if we do that, then what we get is the following. So now let's evaluate that. So first of all, let's look at the constraint equation. So the constraint equation then is going to be the integral from naught to infinity, the density of states in energy, d epsilon, and then the epsilon over e to the beta epsilon minus mu minus 1, and the density of states in energy was a formula that we derived before. So this turns out to be then V over 4 pi squared 2m over h bar squared to the 3 halves times then the integral from naught to infinity. And remember that the density of states has the form epsilon to the 1 half. and then some factors, and then e to the beta epsilon minus mu minus 1. And so that is the constraint equation. So again, double check this if you haven't, if you don't remember before. We went from integral over k to an integral over epsilon using the change of variables. Epsilon is h bar squared, k squared over 2m. That's all we did. You learned how to do that on your mother's knee. So now let's look at some of the. Let's have a look at this function. It's very interesting. So on the right hand side, I've got a bunch of factors, and then I have on the right hand side the integral itself. So I'm now going to write this in the following way. I'm going to then say that I can write this as n over v times 4 pi squared times h bar squared over 2m to the 3 halves. And then that is equal to the integral from 0 to infinity epsilon to the 1/2 d epsilon over e to the beta epsilon, and then e to the minus beta mu, and then minus 1. Now I've written it in this way to drive home for you what it is that the chemical potential does. So let's have a look then at the left-hand side. So here is this left-hand side, and this is just a constant. Okay, now the right-hand side, well, you can see that it has a beta in here and a beta in here. And so those two things mean that there is a beta, i.e. a temperature dependence that is explicit there. So let's have a look at what that temperature dependence does. So as beta goes to infinity, which means we're going towards 0 temperature, so T goes to 0, then this term e to the beta epsilon is then going to go up. Okay, I've got epsilon is just a number, that's just the variable of integration. For any fixed epsilon, as I make beta go to infinity, e to the beta epsilon is going to increase. So if e to the beta epsilon is going to increase as beta goes to infinity, then that means that e to the minus beta mu must decrease to compensate. So we know that the left-hand side does not depend on beta, so the right-hand side can't as well. So therefore, we know that e to the minus beta mu must cancel out the increase due to e to the beta epsilon. And so that means that e to the minus beta mu decreases, and therefore, since mu is less than 0, then what we need, the absolute value of mu, to get smaller. We saw this in the Fermi-Dirac case. As you go to high temperatures, the chemical potential is negative, and it gets larger and larger as the temperature gets bigger. So the same thing is true here. So therefore, as we take the temperature going smaller, meaning beta gets larger, the absolute value of mu gets smaller. And so let's draw a picture of that. So basically, we have a picture like this. So here is temperature, and here is mu, and here is 0. And now what we know from the Fermi case is that mu is large and negative at large temperatures. And what I've just argued for you is that as we make temperature going towards 0, then this thing continues in this direction and goes up and goes, the absolute value of mu gets smaller, but still remains negative. So then we can ask a very interesting question. So here's a question. So eventually, mu as a function of t must get to mu is equal to 0. It's going from large negative number and is going to smaller and smaller negative numbers. Eventually it'll get to 0. So let's ask the question. So when does it get to 0? So the answer for that is, well, okay, just set a beta equals infinity in the constraint equation. And so then we get that n over v times 4 pi squared h bar squared over 2m to the 3/2. Then that equals, the right-hand side is this integral 0 to infinity, epsilon to the 1/2 d epsilon. And now the chemical potential is set equal to 0. So now I just have epsilon over kb tc minus 1. So I'm setting beta, I'm not setting beta equal to infinity. This is wrong. I'm setting mu equal to 0 in the constraint equation. And then we're asking, so eventually mu of t must get to 0. When does it reach 0? So we're going to call the answer, call that Tc. Okay? And we're going to expect that Tc should be 0. But let's see what actually happens. So now I want to compute what that is. So now we're going to solve for Tc. So how do we do that? Well, we're going to use our scaling trick. So we're going to change variables and define x to be epsilon over whatever is the special temperature, KTC. And then what we end up with is n over v times 4 pi squared h bar squared over 2m to the 3/2, and then that is equal to what? So let's have a look at what happens when we change the variables. So now start thinking, wake up, okay? Start thinking, okay? So here's my question for you. The thing on the right-hand side is an integral. I've scaled out I changed the variables. X is epsilon over KTC. So and why did I do that? I did that so that the integral then is just a pure number, has no temperature in it, and then the KTC will then be on the outside of the integral. Okay, how many powers of KTC will be on the outside of the integral? You've answered the question today. Somebody who hasn't answered the question today, or asked the question today. Well, you ask, okay. So we made this change of variables to make this thing be e to the x. Okay, so then I make the change of variables. So then it's going to be, I have to work out the epsilon is x times KTC, blah, blah. How many powers of KTC appear on the front end? Gosh, 3/2. 3/2. Thank you. Right. So this is going to then be KBT to the 3/2 power times this integral. And now I've changed the variables. So now this integral then is now x to the 1/2 dx over e to the x minus 1. Now there's an integral that doesn't depend on anything. It's just a number. And you can look it up in a book of tables, or ask Google, or ask Mathematica, and it's just a number. 2.6 or something like that. Okay, so that's the whole point. You change the variables in such a way that all the physical variables come outside. Here's all the physics, and then this is just a number. And this number is not equal to infinity. It's a number of order 1. Just some number. So what that means then, if I do the integral then n over v is equal to 2.6 times m kb tc over 2 pi h bar squared. There might be a typo here, I'm not sure. To the 3/2. And so therefore I can write down that n over v divided by 2.6 raised to the 2/3 power is equal to m kb tc over 2 pi h bar squared, if I did that right, and therefore I can read off that tc is equal to some blah, blah, blah. Okay. And it's a number, okay? It's non-zero. So now our picture looks really weird, right? So here now, let's put this in. So we've argued that mu is going towards 0. Its magnitude is getting smaller as the temperature gets smaller. And we found that this curve comes in, and then here reaches Tc, and this Tc is not 0, it's some number given by 2.6 and the density and blah, blah, blah. Okay? So that's interesting. So then we have an interesting question. All right, well, what happens if I lower the temperature further? Now the question is, okay, fine. But what happens when T goes less than Tc? Okay, so the first answer you say is, well, okay, so mu just keeps going. So that would look something like this. So here's my graph. This is mu, this is 0, this is t, and then what we're asking is, well, so it did something like this. There's Tc, and then we can ask, well, probably just keeps on going, something like that. Okay, so that would be the question. That would make sense, except it can't possibly be true. It can't possibly be true because remember, we summed, to get the Bose-Einstein distribution, we summed a geometric series. And we summed a geometric series, and so the condition for the convergence was that mu is less than 0. So what that means is that this is impossible. Can't happen. So now we have a problem. What happens? Now? How did we get into this situation? And so we have a problem. Because mu has to be less than 0. Okay, so how many people have seen this problem before? Know this problem? So about 3 or 4 of you. Okay, fine. So you guys be quiet. So the rest of you who are seeing this for the first time, now give some thought to what it is that went wrong. How did we arrive at a nonsensical result? We did everything according to plan. We did everything the way that we'd carefully calculated. with all our grand canonical distributions and our zeta functions and blah, blah, blah. Where did it all go wrong? Where did we make a mistake? Did we make a mistake? Okay, so think about that. Those of you who sort of said you've seen this before, there were like 3 or 4 of you. Do you actually know the answer to my question? You've seen this before. You even know the name for this, right? But you don't know where it went wrong, right? Okay, that's what I thought. Yeah. And if any of you have read ahead in the notes, you'll also know the answer. So don't answer. Okay, Jake.
This, I guess, does it have something to do with the asymptotic expansions we did?
So I showed you the asymptotic expansions, meaning the small z and large z behavior for the function f3 halves for the Fermi-Dirac distribution. But I haven't shown you the corresponding ones for the Bose-Einstein distribution. There are ones like that. There is a b5 halves and b3 halves, and you'll get to do that in the homework. But I haven't used those yet in this argument. Okay. Yeah.
Yes, I have 2 guesses.
2 guesses, okay.
Actually, only 1 guess. I just realized one of them is wrong. It's that like, because the whole reason why the chemical potential has to be smaller than 0 is because E is allowed to be 0.
Yes, because remember E, the energy of the state goes like p squared over 2m, or h bar squared k squared over 2m.
Okay, so it's allowed to, okay, no.
So the energy can go to 0, right? We're just looking at the energy, the kinetic energy of a bunch of 3 non-interacting particles. Okay, Jake, you've had 1 try already. Anybody else got anything to say? Josh.
We turn the sum into integral, but at low temperature, that may not be valid.
Okay, go on. Why might it not be valid?
Because we're summing. The reason we turn the sum into integral is because there are a lot of terms in the sum. There are a lot of energy levels, but at low temperature, the energy levels that gets occupied might be very limited because bosons, they like to stick to a few. They can coexist with each other, so they can just stay in a few states.
That's in the right direction. Yes. So very good. Jake, you had a question. You had an answer too. Before I want to continue with what Josh said. It's not quite. It's in the right direction, but not the whole story. Okay, Jake, did you have another thing?
I like this better.
You like this? Okay. So what Josh said is a very good point. But remember, when we turned the sums into integrals, we didn't make an assumption about the temperature. That was based on being able to say, well, the spacing between levels, between the k states goes like 2 pi over L times the quantum numbers. So we're making the system size going to infinity. So the spacing is getting smaller and smaller. There's nothing special about the temperature in that. Okay, but you're on the right track. So now let me tell you what's the funny thing. Everything is fine. If there was a problem with turning the sum into an integral, we would just get maybe the wrong answer, but we wouldn't get a paradox. But we've got here a paradox. So here's the problem with the paradox. The problem is this: the density of states. So I'm going to tell you what happened. Okay, what happened is this: all the particles went into the ground state. Okay, well, not all of them. Some of them did. Okay, and we neglected the occupation of the ground state. So the reason, so you can say, well, why is that a problem? And I'm going to answer that in detail in a few minutes. But here's the thing I want you to notice. We are doing an integral. Let's look at the left-hand panel. We're integrating from 0 to infinity. And we have in the measure of our integral epsilon to the 1/2. So if something funky happens with the ground state of the system, which is the k equals 0 state, this integral will not detect it. It will not detect it because the ground state has epsilon equals 0. And so that will therefore, because of the numerator, it will make no contribution to that integral. So the Riemann sum will break down just for the ground state. Any of the excited states, you might get a slightly incorrect answer up to corrections due to the size of the system, but you won't get a paradox. Okay, and we'll talk about that. So the problem, so the reason for the problem is part 1 is that the epsilon equals 0 state has unfortunately got 0 weight in the integral. And so in that sense, it is a problem of turning a sum of states into an integral. In that sense, you are right. So that's the unfortunate part. And normally it wouldn't matter. But for t less than tc, a macroscopic occupation of the ground state has occurred. And I'm going to explain that. So there's two things here, and they're logically different, and they need to be discussed separately. I want to particularly talk about what I mean by macroscopic occupation, and then I also want to explain how to fix problem number 1. So problem number 1, in fact, is very easy to address. So we can solve problem 1 quite easily. We just include the ground state explicitly on the right-hand side. So the density of states and energy was a thing that kicked out the ground state because it went as epsilon to the 1/2. So all we do is just simply add it in. So what I'm going to say then is that we'll write down that explicitly. So we'll write down the constraint equation as n equals, and then what we had before was v, whoops, that wasn't very good, was it? What we had before was n is equal to v over 4 pi squared 2m over h bar squared to the 3/2. And then we have this integral 0 to infinity epsilon to the 1/2 d epsilon over e to the beta epsilon minus mu minus 1. So that's what we had before. And now we've realized, well, oops, we forgot about the ground state. So let's put in the ground state. So the ground state is when epsilon is equal to 0. So that number is 1 over e to the minus beta mu minus 1. So that's the contribution from the ground state. And then the other contributions from the excited states are given in blue. So this then is this is the contribution from the ground state. And this is the contribution from the excited states. Okay? So that's how we fix the the problem, and now let me tell you how this fixes the problem. So we will see. I'll explain this going round in circles, as it were. So we will see the following: that for t much greater than tc, the first term is negligible. And so, and is negligible, I should say negligible with respect to what? It's negligible in terms of contributing to the total number of particles in the system n. Okay, so that's true. And what I'm going to show you is that when t gets less than tc, the first term is non-negligible, and not only is it non-negligible, but mu then is still less than 0, but not exactly equal to 0. So in other words, the picture is going to be, what I'm going to show you is that it's not true that mu equals 0 for t less than tc. It is close to 0, but not exactly equal to 0, and I'm going to quantify that right now. But the only way that we can resolve this problem is if this happens. So now let's see how this works. So how does this work? How does this guess work? So the way this guess works is the following. If I say that if mu is less than 0, but very small, then I can expand the first term, 1 over e to the minus beta mu minus 1. So this then is approximately 1 over 1 minus beta mu plus something of order beta mu squared minus 1, and that then is equal to minus kBt over mu. And this quantity on the left-hand side is the number of particles in the ground state, and I'm going to call that equal to n0, and I'm going to call this n epsilon for excited states. So this then is the number of particles in the ground state, and that goes like this. Okay, now, why is that important? Okay, so what? Well, now let us suppose that the magnitude of mu is something that scales with 1 over the volume of the system. Okay, let's just suppose that that were the case. Okay, why? Well, then what that says is that n naught over v then is a number that is of order 1. So mu is going like 1 over v. So n naught over v is something like minus kBt, something like that. So it's a thing that is independent of n naught and v. It's just a pure number. And so that says that there is a fixed fraction of particles in the ground state. So it's not that there's 100 particles in the ground state. What we care about is, as I make the system bigger and bigger, does the number of particles in the ground state scale with the size of the system, just as so that the density stays constant. And this idea that the chemical potential below Tc is a number that scales as 1 over V would allow that to happen. So there's a fixed fraction of particles in the ground state. So as we take the thermodynamic limit, and so that fixed fraction of particles is not the same thing as a fixed number. If you tell me I've got 100 particles in the ground state and I make the system size going to infinity, I can ignore the ground state. If you tell me that there's always going to be a fixed fraction of particles in the ground state, as I make the system bigger, the number of particles in the ground state also grows. And so it's always occupied in a way that is a fixed fraction of the number of particles in the system. So let me come to your question in a second. So what that means is, as we take, as V goes to infinity, N over V equals the particle number is equal to a constant, and N naught over N also equals a constant. And if it were different than this, if on the other hand, N naught did not scale like the volume, then N naught over N would go to 0 as N goes to infinity. And that's indeed what happens at high temperature. So was it Eric? So, sorry, Jing, sorry, so sorry.
So when you are expanding the exponential under the n naught, so you have to assume that beta times mu.
Yes, that's right.
So now that I can see that when mu is very small, but when the temperature reaches 0, that means beta goes to.
Right. Right. So we're not setting beta equals to infinity. So you tell me what beta is. You tell me what temperature you're at, and then I make the system size go to infinity, and mu varies as 1 over the system size. So for fixed temperature, now I take the thermodynamic limit. Okay. So then you might say, okay, all right, well, fine. So what is the occupation of the excited states? For T less than Tc. So let's work that out. So we know that epsilon is h bar squared, k squared over 2m. We know that k is like 1 over 1 over the volume to the 1/3 times the quantum numbers. Volume to 1/3. Remember that each component of the momentum goes like k is 2 pi over L times the quantum numbers. L is the volume to the 1/3 power. So therefore, this is a quantity that scales as V to the minus 2/3. And so what that means is then the occupation number of a state with energy epsilon of k is then expectation value of nk is equal to 1 over e to the beta epsilon of k minus mu minus 1. And then this thing, so now I can write this as, I'll write it down here. I can write this as, roughly speaking, 1 over beta epsilon, and then beta times mu. So beta epsilon scales as v to the minus 2/3. So this is going to be 1 plus a term that is order v to the minus 1/3. And then that then basically goes as v to the 2/3. And so therefore, the expectation value, the occupation number of any state with wave number k is nk over v, then will go as v to the minus 1/3. Okay, so let me just go through that exactly what I did just to be sure. So we know that epsilon itself scales as v to the minus 2/3. That is the epsilon that is in here. On the other hand, we know that mu, we know that mu that is in here, that scales as v to the minus 1. Because I'm looking at the excited states for t less than tc. So therefore, the term epsilon going as v to the 2/3 and the term v to the minus 1. So I can then take out the epsilon. This term over here, this v to the minus 1/3, is basically mu over epsilon. And mu over epsilon, since mu goes as v to the minus 1, and epsilon goes as v to the minus 2/3, so that's v to the minus 1/3. And so therefore, the expectation of nk scales as v to the 2/3, and therefore the whole thing scales as v to the minus 1/3. So what that means is that the occupation number not the occupation number. The number density of each excited state goes to 0 as I take the thermodynamic limit. But the sum of all of those is non-zero on scales like n. So that's all fine. But the ground state for the ground state, m naught over v is a number of order 1 as v goes to infinity. And so the ground state is macroscopically occupied. And the number density of each excited state, the excited states are not macroscopically occupied. And so this phenomenon has a name. This is called Bose-Einstein condensation. It's called Bose-Einstein condensation because Bose figured out the Bose-Einstein distribution, and Einstein figured out the Bose-Einstein condensation, the thing I just showed you. So as far as I remember, that is the history. So basically, what's happening here is mu over epsilon is of order v to the minus 1/3. And so that means that we can neglect mu over epsilon when we are looking at in that term in the integral. Okay, so so now let's write down more precisely what is n naught. So now let's calculate more accurately. So now I've given you the general physical picture. Now let's calculate it a little bit more accurately. So now we're going to look at what happens when t is less than tc. And now I want to know, what do I do to compute the number of particles in the excited states? And the answer for that is, well, since mu over epsilon is of order v to the minus 1/3, when t is less than tc, I can set mu equals 0 in the Bose-Einstein formula. And so then what I get then is that n as a function, n epsilon, the number of particles in the excited states, is v over 4 pi squared, 2m over h bar squared to the 3/2, times the integral from 0 to infinity, epsilon to the 1/2, d epsilon over e to the beta epsilon minus 1. Now, you've seen this integral before. This was the integral we did to calculate the Bose-Einstein condensation temperature. And this integral, though, now has beta in it, not 1 over kTc. So when we computed the Bose-Einstein condensation temperature, bless you. You had epsilon over kbtc, but now we have epsilon over kbt. So it's the same integral. So then we know then that what that means is that n epsilon then is equal to 2.6 times v times m kbt over 2 pi h bar. There may be a squared missing, I'm not sure, to the 3/2. Maybe something like that. I'm not sure. You'll have to check it. And so in any case, that is going to be n times t over tc to the 3/2 power. And then the number of particles in the ground state, so therefore n naught is equal to n minus the number of particles in the excited state, then is going to be n times 1 minus t over tc to the power 3/2. And so now we've seen that that what happens is as I go below this temperature, Bose-Einstein temperature Tc, what happens is above it, there's no particles in the condensate, there's no particles in the ground state, everything is in the excited state. And then as I go up from there, then this is going to rise like, actually, what is it going to do? It's going to go to 1 up here, and it's some function that comes in like that. Right? Does it go in like that, or does it come in the other way? No, I've forgotten. somebody smarter than me can figure it out. Okay, so now let's compute the thermodynamics. So now I can work out the energy and heat capacity. So for those, missing the ground state doesn't matter because the ground state just got energy 0. So I can work out the internal energy, the expectation value of the energy is then just naught to infinity epsilon times the density of states in energy d epsilon over the Bose-Einstein distribution. This is below TC. And that that is V over 4 pi squared 2m over h bar squared to the 3/2. How many powers of kBt are going to come out of this integral? Do it in your head.
No.
Not 2. No. Okay. 5/2. Thank you. Yes. As before, before we just have this times this, we've got another one. That gives us 3/2. So we've got another one. So that gives us 5/2. Okay. So it's going to be a number. So it's kBt to the 5/2. And then the number that it's equal to is the integral from 0 to infinity x to the 3/2 dx over e to the x minus 1, and that's just some number. And so what you end up with then is 0.77 nkb times t over tc to the power I think there's a mistake here in my notes. I think it's 5/2. Okay, and then if I work out the heat capacity, so then you end up with 1.9 nkb T over Tc to the 3/2. And so I can plot that over here. So here is T over Tc. Here is Cv over nkb. And if it was a classical gas, it would be 3/2. So we know that at high temperatures, this graph should definitely be going like this. But in fact, what happens is this thing comes up like that. And then there's a cusp, and then it comes around like that. And it sort of looks like a phase transition. In mean field theory, it's basically it's a sort of first order transition. Anyway, so I'm not going to go into that for now. So there's a sort of cusp non-analyticity. And some books say it's a third order phase transition. That's not quite correct. Okay, so I think that's pretty much where I'm going to stop. We're nearly out of time, but I've got a few minutes left. And so I want to just introduce the next topic. So that's all I want to say about Bose-Einstein condensation. It's super interesting. And in the next homework, I'll give you a bunch of exercises to do on that. Can I take, is your question urgent or can I take? Okay. So what I would like to do now is I want to start the next topic. Up to now, all our systems have been particles bouncing around in a box. And now we're going to talk about another paradigm system, which is not particles bouncing around in a box. it's spins, quantum spins that are sitting in a system, and we want to try to understand what is the behavior of spins. So I want to just introduce for now the system, and then next time we will work on it. So the next topic is paramagnets, and what we're going to do is so this is the sort of spin equivalent of ideal gas. So what do I mean by that? Well, in ideal gas, you had particles that bounce around. They certainly bounce off the walls of the container, but they don't interact with each other. So they're non-interacting particles. So they're the spin equivalent of ideal gas, i.e. non-interacting spins. And the non-interacting spins are just in the same way that the particles bouncing around in the box bounced off the walls of the box. So there was an interaction with what's keeping them in the box. So the spins interact with external fields like electrical or magnetic fields. And so there's no interparticle interactions, no interspin interactions, but there are interactions with external fields. So they're non-interacting spins, but they can interact with external fields. And so what we're going to do in this section is we're going to look at the quantum and classical behavior of magnetic dipoles, which are what spins are. And the system, what are those systems? So here's the picture. So here's my box. Now, not particles bouncing around in the box. It's a bunch of spins. So I'm going to write those spins like this. There's an atom, and there's a spin vector associated with it. Here's another atom, a spin vector associated with that. Here's another atom, a spin vector associated with that, and so on and so forth. And then we're going to have an external magnetic field like that. And we're going to draw our coordinate system to be like so. So this will be X, Y, and Z. And there's materials that do this, and I'm going to just next time I'll begin by telling you what they are and what are their quantum numbers, because those quantum numbers turn out to be interesting in terms of the predictions that we can make. Okay, so that's finished for today. And let me just turn off the recording, and I'll be happy to take any questions.